We just solved our first ever RLC circuit using Laplace transform in the previous video. Now we want to analyze a little bit what does it mean and what else we can learn using Laplace transform. So you have seen that if you apply Laplace transform, you get that equation, which is in effect an algebraic equation for unknown function I bar. And you can write it as this bracket times a Laplace transform of I, which is exactly I bar. So that's just a different notation. And on the right hand side, you can write a Laplace transform of an input in the applied voltage. You can also call it U bar. So we just did nothing but just written this in a slightly different form. But what it suggests you is that you can think that you want to go from an input, which is the voltage you apply to your circuit, to the current. So in some sense you want to know how the circuit responds to applied voltage. And indeed, you have seen in a previous example that if you apply a voltage which just turns at time 0 and stays at a constant level, so this is your voltage U as a function of time, so you switch it on at time 0 and then it stays constant, then your circuit will produce an output which is the electric current, which responds to that with some excitation which then decays. So you get a response which dies out. And Laplace transform is a clever way to try to understand how your RLC circuit would respond to any kind of input, not just to that particular type of input, not just to the unit step. And what you can do, you can say, let's look at the Laplace transform version of that. So you have a Laplace transform of U and a Laplace transform of the current. And there is a way to directly connect these two using what we call a transfer function. And you can see it here. So it's a function which effectively just multiplies your input to get you an output. And in other words, the transfer function is just the ratio of your output, which is a function of s, to your input, which is also a function of s. And that's quite useful and generic. In our particular case, you can see that is exactly is the transfer function. That is g of s, but inverse. reciprocal, sorry. So it's 1 over g of s. Because if you will move it to the other side, you'll see exactly that kind of expression. And you can simplify it to write as s over 2s squared plus 8s plus 40. So as I said, that this is a generic approach. So you take any input to your circuit and the transfer function will tell you how this will produce an output. And that is again a definition which I want you to bear in mind, because this will be important for answering questions. So if somebody asks you, find a transfer function for an electric circuit, you apply Laplace transform to the equation describing the circuit, and then you identify what is the input, what is the output, and what is the part which connects a Laplace version of the input and a Laplace version of the output. So ultimately you need to connect the Laplace transform of I to Laplace transform of U. So normally what you do is you do your transform and identify what exactly this bracket in a factor of I bar is. So if you have something times I bar equals to the U bar, then that something is just the inverted transfer function. And sometimes it's denoted using different symbol, for example Y or even H sometimes. And other parts of kind of pairs of inputs and outputs are possible as well. And it's very important in signal processing. And one more important thing I want you to bear in mind is there is also a response function in addition to transfer function. So if you have a unit impulse input to your circuit, which produces an output, let's call it g of t, that output is called a response function. And what's really useful about it is that it's equivalent to studying, instead of an ODE equation which describes an RLC circuit, you can look at the algebraic equation if you use a Laplace transform. So if you apply a Laplace transform, then instead of unit impulse, which is a delta function, you'll get just 1, and that will produce you a transfer function as an output. So thing to bear in mind that if you know the response function, you know the transfer function. If you know the transfer function, you know the response function. And they're connected as follows. So if you take an inverse Laplace transform of the transfer function, you get the response function. So now you know how to find a transfer function of electric circuit and how to find a response function of an electric circuit. And the difference that the transfer function will depend on S, while the response function is actually a physical response to a unit impulse, depending on time.